Welcome to Calculus with the Pack. Today Fennec, Wolfy, Luna, Urso, and Rascal are going to walk you through the entire foundation of calculus. Derivatives, integrals, and everything in between. Let's go. So what is calculus? Calculus is the mathematics of change and accumulation. It was developed by Newton and Leibniz in the 1600s, and it completely changed science, engineering, and mathematics forever. There are two branches. Differential calculus asks, how fast is something changing right now? Integral calculus asks, how does something accumulate over time? And here's the magic. These two branches are exact inverses of each other. Keep that in mind. Everything we cover today connects back to it. Before we can talk about derivatives, we need limits. A limit answers this question. As x gets closer and closer to some value a, what value does f of x approach? We write it as the limit of f of x as x approaches a equals L. Notice x approaches a, it doesn't have to equal a. We also have one-sided limits. Approaching from the left uses a minus superscript, from the right uses a plus. Both sides have to agree for the full limit to exist. Let's make it concrete. Take f of x equals x squared, and let x approach 2. At x equals 1.5, x squared is 2.25. At 1.9, it's 3.61. At 1.99, it's 3.96. Coming from the other side, 2.01 gives 4.04, 2.1 gives 4.41. Both sides squeeze toward 4. The limit is 4. Now the derivative. The derivative is the instantaneous rate of change. Think of a car speedometer. It doesn't show your average speed over the whole trip. It shows exactly how fast you're going right now. Formally, the derivative f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Geometrically, that fraction is the slope of a secant line connecting 2 points on the curve. As h shrinks to 0, the second point slides toward the first, and the secant line rotates until it just touches the curve. That's the tangent line, and its slope is the derivative. You'll see it written three ways: f prime of x, dy over dx, or d of f. They all mean the same thing. The power rule is the most used rule in all of calculus. Learn it cold. The rule, d over dx of x to the n equals n times x to the n minus 1. 2 steps. Bring the exponent down as a multiplier. Then reduce the exponent by 1. Examples: x cubed becomes 3x squared. X to the 5th becomes 5x to the 4th. X squared becomes 2x. X becomes 1. And any constant has a derivative of 0. Constants don't change. The chain rule handles composite functions, functions inside functions. The formula, the derivative of f of g of x equals f prime of g of x times g prime of x. Differentiate the outside, leave the inside alone, then multiply by the derivative of the inside. Example 1, d over dx of sine of x squared. Outside is sine, its derivative is cosine. Inside is x squared, its derivative is 2x. Answer, cosine of x squared times 2x. Example 2, d over dx of the quantity 3x plus 1 to the 5th. Outside, power rule gives 5 times the quantity to the 4th. Inside, derivative of 3x plus 1 is 3. Answer, 15 times the quantity 3x plus 1 to the 4th. Every time you see something inside something else, think chain rule. 2 more rules. The product rule handles 2 functions multiplied together. F prime g plus fg prime. Memory trick. First d second plus second d first. Example, derivative of x squared times sine x. First d second, 2x times sine x. Plus second d first x squared times cosine x. Done. The quotient rule handles division. F prime g minus fg prime, all over g squared. The mnemonic, low d high minus high d low, over low squared. Say it out loud a few times, it really sticks. Now we flip to integration. The key idea, to find the area under a curve, chop it into thin vertical rectangles. Each has a small width and a height equal to the function value. Add them all up. The more rectangles you use, the more accurate you get. At 6 rectangles, it's rough. 50, pretty good. At 200, you can barely see the gaps. In the limit, As the width of each slice goes to 0 and the count goes to infinity, you get the integral. We write it with a stretched s symbol f of x and dx. The s stands for sum. F of x is the height of each infinitely thin slice. Dx is the width. Integration rules are the reverse of derivative rules. The power rule for integration, integral of x to the n is x to the n plus 1, divided by n plus 1, plus c. Raise the exponent by 1, divide by the new exponent. Integral of cosine x is sine x plus c. Integral of sine x is negative cosine x plus c. Integral of e to the x is e to the x plus c. E to the x is its own antiderivative. Integral of 1 over x is the natural log of the absolute value of x, plus c. Integral of a constant k is kx plus c. And always, add plus c to an indefinite integral. That c represents any constant that could have been in the original function. It's not optional. A definite integral has bounds and gives you a number, not a function. The formula. The integral from a to b of f of x dx equals f of b minus f of a, where capital F is the antiderivative. Let's work it. Integral from 1 to 3 of x squared dx. Antiderivative of x squared is x cubed over 3. Evaluate at 327 over 3 equals 9. Evaluate at 1 over 3. Subtract. 9 minus 1/3 equals 26 thirds. Roughly 8.67. That number is exactly the area of the shaded region under the curve between x equals 1 and x equals 3. Now the crown jewel, the fundamental theorem of calculus. This is why Newton and Leibniz's work was so revolutionary. It reveals that differentiation and integration are perfect inverses of each other. Part 1. If you integrate f from a to x and then differentiate the result, you get f back. The derivative undoes the integral. Part 2, the one you'll use constantly. The definite integral from a to b of f of x equals f of b minus f of a. This lets us evaluate integrals without dealing with Riemann sums at all. Find the antiderivative, plug in the top bound, subtract the bottom bound. Differentiation and integration are like opposite directions on the same road. One undoes the other completely and perfectly. Let's zoom out. Why does any of this matter? Calculus is everywhere. In physics, velocity is the derivative of position and acceleration is the derivative of velocity. Every rocket ever launched used those relationships. In biology, exponential population growth is modeled by a differential equation that requires calculus to solve. In economics, marginal cost, how much one more unit costs to produce, is the derivative of the total cost function. In medicine, the concentration of a drug in the bloodstream over time is calculated with definite integrals. In engineering, areas, volumes, and work almost always require integration. And in machine learning and AI, gradient descent, the algorithm that lets neural networks learn, is built entirely on derivatives. Every time a model updates its weights, it's doing calculus. Calculus is not abstract math for its own sake. It's the language the universe is written in. Now let's practice. Try each problem yourself before I give the answer. Problem 1. Find the derivative of 3x to the 4th minus 2x plus 7. Power rule on each term. 3x to the 4th gives 12x cubed. Negative 2x gives negative 2. The constant 7 disappears. Answer. 12x cubed minus 2. Problem 2. Find the derivative of the quantity x squared plus 1 to the 3rd power. Chain rule. Outside, power rule gives 3 times the quantity squared. Inside, x squared plus 1 has derivative 2x. Multiply them. Answer. 6x times the quantity x squared plus 1 squared. Problem 3. Find the integral of 4x cubed plus 6x dx. Reverse power rule on each term. For x cubed integrates to x to the 4th. 6x integrates to 3x squared. Plus c. Answer x to the 4th plus 3x squared plus c. Problem 4. Definite integral from 0 to 2 of x squared minus x dx. Antiderivative x cubed over 3 minus x squared over 2. At x equals 2, 8/3 minus 2. At x equals 0, 0. Subtract. 8/3 minus 6/3 equals 2/3. Answer 2/3. Problem 5. Find the derivative of x cubed times e to the x. Product rule. First d second x cubed times e to the x. Plus second d first, e to the x times 3x squared. Factor out x squared e to the x. Answer x squared e to the x times the quantity x plus 3. Let's recap. Limits tell us what a function approaches as x gets close to a value. They're the foundation everything else is built on. Derivatives measure instantaneous rate of change. The power rule, chain rule, product rule, and quotient rule are your toolkit. Integrals measure accumulation, the area under a curve, and they're the reverse of derivatives. The fundamental theorem of calculus ties both branches together. Differentiation and integration are perfect inverses. 3 formulas to memorize and never forget. The definition of the derivative. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. The power rule. D over dx of x to the n equals n times x to the n minus 1. And the fundamental theorem. The integral from a to b of f of x dx equals f of b minus f of a. That's calculus with the pack. You've got the whole foundation now. Practice problems every day, go slowly on the things that feel hard, and it will click. The pack is proud of you. Keep going.